Welcome to the internship program. I am Shubham Gupta from NextGen AI Frameworks Private Limited. I have more than 14 years of work experience in the fields of artificial intelligence, software development, and robotics. This video is part 3 for Transfer Learning project. Let's continue. In a previous session, we were discussing about transfer learning, what it is. I will give a brief introduction about the project we are doing and what is transfer learning. So in simple words, what transfer learning is, you already have a pre-trained model in your system, for example, which was trained on more than 10 million images. So for training that kind of model, you will require a heavy uh, compute engine. So for example, you will require a machine 20 lakh or 25 lakh rupees machine that will run for 1 month to train a model. For collecting the 10 million images or 1 crore images, you will require lot of effort and lot of time. So what is a transfer learning? Transfer learning helps you in accelerating the training process. You will use a base model which was already trained on that kind of data set, and using that as a base model you can train your own model in less time. I will show you what is happening in this project and how we are using the transfer learning to train the model. Okay, so let's start the server. Have used UVcorn for this project. So it is starting the server on 8000 port. Okay, so what happens is I created this API using this, and when I will pass image of cat or dog. So for example, I have this cat image, and when I submit this into the model, it is telling the prediction is cat, and if I give the image for dog, it is showing prediction of dog. So this is what is happening here, but just look at this, how much time this model will take to uh, how much time it will take to create the model. So let's see, python main.py. Done, model was trained. So what is happening, it is using a base model, that is in our case ResNet 18. So this is already a pre-trained model that we are using as a base, and removing the last fully connected layer and replacing the layer with our own helps us to modify the model as per our requirement, that is detecting the cats and dogs. So how it is doing it? It is using a base model ResNet 18. So I will show you this. I have mentioned in the article. Okay, so I will just search on Google ResNet 18. So it is a CNN 18 layers deep, and it was pre-trained and can classify images up to 1000 object categories. It can detect 1000 object categories such as keyboard, mouse, pencil, and many animals. So this is the base model that we can use to train our own model. Okay, so for setting up the project, I told you you have to set the virtual environment. Then comes the part of data preparation and transformation. So I will repeat how you need, in what format you need the data. So I have created this data directory. In this data directory I have test and train directory. In train directory I have classes names as the directory. So for example, all the cats images are in cats folder, dogs images are in dogs folder. Similarly, in the test folder we have cats and dogs folder. So this will be the base format, how you keep the data for the training and testing. Okay, so you will look at this code from Torch Vision import transforms and this code. So what this is, this code block is creating a dictionary called data underscore transforms, which defines two sets of transformation, one for training data, one for testing data, training data, testing data. Both transformations are identical here, but setting them separately allows you to easily modify them later if necessary. So let's see what this is. Transforms.compose combines multiple transformations into a single operation. Each transformation will be applied sequentially. And what are the transformations? One is resize, to tensor, and normalize. So resize each image to a fixed size of 224 by 224 pixels. This size is commonly used as the input for many CNN like ResNet, as they are often pre-trained on images of this size. So if you see the data I have, all the image sizes are different. So if I look at this image, if I look at this image, look at the options, details, and dimensions are 832 by 555. And if I look at this one, 1920 by 1080, so sizes of images are different. So you will have to normalize the data by converting the data to 224 by 224 pixel images, because the ResNet and most popular CNN are using this same format. And transform.toTensor, what it is doing is converts the image to a PyTorch tensor format. Additionally, it scales the pixel values from the range of 0 to 255 to 0 to 1, which is necessary for consistencies in neural network. So it will normalize the data, convert it to tensor. Then part comes the transforms.normalize, normalize the image tensor to have a mean and standard deviation. Okay, so here I mentioned that ImageNet that we are using here requires data to be normalized in this format, which helps the transfer learning on pre-trained model, as they expect inputs normalized this way. So this is their format. You have to normalize the data. So first step is to resize, convert to tensor, then normalize it. So these are the transformations, data transformations that you have to apply to your data. Comes the part of loading the data set. We use image folder to load images, which automatically assigns labels based on folder name. So let's see image folder, datasets.image folder. Where is dataset coming from? Torch Vision. So let's see the code. So this is the Torch Vision. Here we are getting datasets. Okay, so from datasets use image folder, and it will gather all the images from the folders. And what are the folder names? Train and test. You have to pass those here, and the main data there is data test train. So you have to pass in this particular format. Data underscore is equal to data. What it means is this, we are giving this main directory, then loading it. You can easily read the code and understand it. From datasets.image folder you are getting all the, from these two folders you are gathering all the data and storing in image underscore datasets dictionary. Datasets.image folder loads image from directories and applies the specific transformations. Dataset expect subdirectories named according to the class labels. So remember this, the name of the classes that you want to detect. If you can you see here the output, it is giving dogs. So here I have given the dogs as the folder name. So these should be your classes name. Remember this. Images are loaded with transformations ensuring the images are resized, converted to tensor and normalized. So you can see data transformations are also being written here or used here. So all the transformations that we gave here will be applied to the data. This is the data loader part. So this was the image data set, getting all the images and saving in this dictionary. Then we have the data loaders here. So data loader wraps the dataset iterable objects, allowing each batch processing during training and testing. So we have a dataset containing our images. It will create batches of 32. I have mentioned this here. So what this code is doing, loading all the data here, but with a batch size of 32, load images in batches of 32, which is useful for batch processing in neural network. So you understand, if you are dealing with millions of images, you will need to create batches that you can send. So either you process one by one image, or either you can process 32 images at once. So this is the batch size. And what shuffle equals to true is doing, shuffles the data at each epoch to improve model generalization during training. So if you have cat image 1, cat image 2, cat image 3 in this format, the next time it will become 2 1 3, next time it will become 3 2 1, for example. So it will shuffle the images again and again, or data again and again. This is what shuffle equals to true is. And why are we doing this? For testing, this doesn't impact the outcome but provides consistency in data handling. So when you shuffle the images and it trains in each epoch, it will generalize the model better, means the better you will get better output from the model if you shuffle the images again and again. Dataset sizes and class names, this is the code, and what they mean is, dataset size is a dictionary that stores the number of images in the train and test dataset, allowing for accurate tracking of dataset sizes. We are looking for the length of the images. So if I have 3 images for cat, 2 images for dog, so dataset sizes will store which class or category contains how many images. So dataset sizes. Class names, here what they are including, retrieves the class labels, directory names within the trained dataset, which is useful for interpreting model predictions later. So you understand this, why dog is coming, because we are storing the classes name and binding them with the class numbers, so that the output we get should be in the form that we can understand. If I give 0 1 here, you won't be able to remember if you have 1000 classes. So giving the labels makes more sense. Setting up the model. So I told you the base model we are using is ResNet 18, and the reason also I told you why we are using a pre-trained model here, because this is transfer learning and we want to save time. So ResNet 18, a popular model for image classification, modifies its final fully connected layer to match the number of classes in our dataset. How many classes we have? We have 2 classes right now, cat and dog. So what this line is about, loads a pre-trained ResNet 18 model which has already been trained on the ImageNet dataset. Using a pre-trained model allows for leveraging previously learned feature, which is particularly useful for if the new dataset is similar to ImageNet in terms of general image features, example objects, textures, etc. So if it contains some classes, animal classes, model contains animal classes, so those things will be similar, but from the last layer, fully connected layer, we will just add our own layer. So pre-trained equals to true. This argument indicates that we want to load the weights from a model that has been trained on ImageNet, which significantly speeds up training and improves accuracy in transfer learning tasks. So pre-trained to true because this was pre-trained. Extracting the number of features. As you know, features can be edges and all those things that I told in earlier sessions. So the final layer of ResNet 18 is a fully connected layer that maps the model's features to the number of classes in the ImageNet dataset, and in ImageNet dataset we have 1000 classes available. What model.fc.in features gives, it gives the number of input features for this final layer. This number of features represents the output of the last convolutional layer, which is flattened and fed into the fully connected layer. Replacing the final layer, how do you replace it? This is the line. So it replaces the original final fully connected layer with the new one that maps to the number of classes in your dataset. So if you have two classes, they will be passed here because we are doing length of class names, and if you have two class names available, it will give two length. So this is what last layer is, fully connected layer FC, and we are changing it according to our requirement. We have two classes, we will pass two classes, and last fully connected layer will be ours. So by doing this, we tailor the model to our dataset, changing the output layer to match the number of classes in the new classification task while retaining all the other layers. Now comes the part of defining. Okay, so I will show you the code also. In code I have written all these things, so now you understand this, why we are using data transforms, data dir, image datasets. These are the class names that we are storing, and here we are passing the class names. So this is the final layer that we are modifying according to our requirement. Now let us look at more code. So what this is: define the loss function and optimizer. In our classifier we will use cross entropy loss and SGD optimizer with the learning rate of this. So these are the code, and what they mean is this. This is the commonly used loss function for multi-class classification task. If you remember, I told you this many times in previous projects also about cross entropy. It combines logsoftmax and NLL loss in one single class, so you don't have to go too deep into it, you just have to use it. There is mathematics involved in these things, so if you want to go deeper you can learn more about them, but it depends on which project you are working. For this project I am just using these to train my machine learning model. So purpose is cross entropy loss measures the difference between the predicted probabilities and the actual class labels. So the prediction and the actual results, it will compare the differences. Minimizing this loss helps the model improve its prediction. So you have to minimize this loss. Torch Optim SGD, stochastic gradient descent for optimization. So whenever you read this word gradient, what it means is changes in the data. Changes in the data is the gradient. Changes in the data. So SGD updates the model weights based on the gradients of the loss function with respect to each parameter. So this one word, whenever you get, remember this is changes in the data. Model.parameters, this tells the optimizer which parameters of the model it should update during training. So model.parameters, which it should change, which parameters it should change, since we replace the final layer and potentially unfroze other layers. Unfroze other layer means we are using all the other layers, but just final layer we are replacing. So this will update only the specified trainable layers. LR equals to, so this is LR is learning rate. The learning rate is a scaling factor that determines the step size for each update. Small learning rate help model converge gradually. This means better output. So momentum 0.9, it essentially keeps track of the previous gradient direction and scales the current gradient update accordingly, making convergence faster and more stable. remember this word faster. So to train model faster. I will continue this session in next video. See you in next video. Have a nice day.